Okay, so let's get started. So today what we're going to do is we're going to talk about isometries and killing vectors, and we'll utilize some of the ideas that we've developed so far. Okay, the idea about diffeomorphisms and flows generated by vector fields. Okay, so so first let's start. So this is going to be based on Nakahara, section 7.6 and 7.7. Okay, so what we'll do is we'll start with a manifold, but now we're going to introduce a metric on this manifold. So till now, everything we've done in the last 2-3 classes, we had only a manifold without a metric. Now we'll ask what happens when we have a metric G on a certain manifold. So the idea is very simple. So we have a manifold M with a metric G, and we take a map F, okay, from this manifold to itself. Okay, so to the same manifold M, and let's say you have the same metric G on this manifold. Okay, now, so what does the transformation F do, or what does this map F do? It takes a point P in the manifold and maps it to another point F of P. Okay, so this you can either think of it as the same manifold or a copy of the same manifold, right? On which you're taking one point P and taking it to another point F of P. Okay. And also because F, we're assuming that F is a diffeomorphism, so the inverse map F inverse will also exist, which will take us from F of P back to P. Okay, and this will be true for any point P on the manifold M. Now, there is the metric GP, okay, which is the metric at the point P, and there is the metric GF of P, which is the metric at the point F of P. Okay, if I'm given a metric, then I know what the metric is everywhere on the manifold. Okay, and the metric is a 0-2 type tensor, and we're saying that there's a particular 0-2 tensor here, which we denote as GP, and there's a particular 0-2 tensor here, which we denote as GF of P. Okay, and this exists because we're considering the same manifold with the same metric. Okay, now what we'd like to do is we want to talk about a special class of diffeomorphism. So F is so this is very general, okay, and for any F, any diffeomorphism F between the manifold to itself, you will induce this kind of transformation. But now we want to take a special class of diffeomorphisms. The special class of diffeomorphisms is such that if we've seen that if you have a map F like this, and if I have a 0R form, or in particular a 0-2 form, which is the metric, I can pull that 0-2 form back using this transformation F. It induces a map which we denote as F star, which allows us to pull back 0R type tensors, or in particular 0-2 tensors. So what we're going to do is we're going to pull back this GFP. Okay, so this is a particular 0-2 tensor. What is the space in which it exists? It exists in the dual tangent space at F of P. Okay, so it exists in the tensor product space of the dual tangent space at F of P. What we're doing when we pull it back is we're finding a corresponding tensor, okay, at the point P. That is, we find a tensor belonging to the point P, okay, that corresponds to this GF. In general, the tensor that we get after pulling back will not be the same as this GP. Okay, we'll get a different tensor. However, for special classes of transformation F, okay, those two things will be exactly the same. So so in an equation, if I pull back G of F of P, and if that equals G of P, okay, so the pullback of G of F P is this, if this is equal to GP, and this is true for all points on the manifold, then this special class of transformations, or the special transformation F, okay, is called an isometry. Okay, iso meaning same and metry meaning metric, so it's the same metric, or you preserve the metric under this pullback operation. Okay, so not every transformation F will guarantee this outcome. There are, given a metric G on the manifold, only certain transformations F will, or certain diffeomorphisms F, only a certain set of diffeomorphisms will actually satisfy this condition where they preserve the metric under pullbacks. Okay, so those are what we're going to call isometries. Okay, and there is an equivalent way to think about isometries. Okay, which is if you have two vector fields x, y, which are vector fields on M. Okay, so I have now a vector x and a vector y. Okay, and this is at one point on the manifold, but these are defined at every point on the manifold. And now if instead of pulling back the metric, okay, I instead push forward the vectors x and y. Okay, so we've seen that there's also a map f star, which pushes forward vectors f lower star. And so I get some vector x and some vector y. Okay, and this is the push forward. Okay, so this is f star x and this is f star y. Okay, note that again, the push forward f star x and f star y, these are not the same thing as x at f of p. Okay, or y at f of p. These are different things, right? Okay, because this is a diffeomorphism f, it means that there's a point p here and there is a would-be point f of p here, which I can think of it as this point p gets mapped to this f of p, or I can think of a copy of the manifold where this point p gets mapped to that f of p. Now, at every point on the manifold, if I have a smooth vector field x, there's also an x at this point, okay, which is xf of p. But this xfp, sorry, it's not really visible. Let me just draw it here. Okay, this is a vector xfp, but this vector xfp is not the same as the push forward vector. Okay, these two may not be the same thing. However, okay, if it is true that the inner product of f star x and f star y under this metric gf of p, okay, note that this is not a push forward or pullback. This is g at the point f of p. So if I take g f of p acting on f star x, f star y, this is the inner product constructed out of the push forward vectors. Okay, if that inner product is the same as the inner product of xy at the point p, that is, if it's this the same as this, then also, okay, this is an equivalent way of saying that f is an isometry. Okay, both of these will give rise to the same thing. You can show that the left-hand side of this, that is gf of p, f star x, f star y, this is the same as instead of pushing forward x and y, we just pull back g, okay, and we take the inner product on x, y. So, so it's an equivalent statement to say that, and if this is true for any arbitrary vector fields x, y, okay, then basically what you're saying is that pulling back the vector, the metric g, preserves the original metric, okay, or in other words, f preserves the norm of the inner product of two vector fields. So if I have two vector fields here and I take the inner product and then I push them forward after a diffeomorphism and then I take the inner product, but inner product with which metric? Not there's no way. I mean, I can define a push forward metric, but that's not what we're doing. We're just taking g of fp and then taking the inner product. Okay, and if that inner product using the push forward vectors and g of fp, if that inner product is the same as this inner product, then we say that that the transformation f is an isometry. Okay, so isometries are specific to the metric that we have on a manifold. Okay, so there's no way to talk about isometries if you don't have a metric. Okay, so if you have a metric on a manifold, then there's a class of diffeomorphisms which get picked out. You can always have any arbitrary diffeomorphism, but certain special diffeomorphisms are the ones which preserve the inner product of vectors, or equivalently, the pullback of the metric remains the same. Okay, so these are equivalent definitions of what we mean by an isometry. Any questions here? Okay,
Sir,
yeah, go ahead, Professor.
how is the last equal? How does the last equality hold?
This one?
Yes, yes.
Yeah, actually, we kind of use this to define the pullback. If you recall how we define the pullback of any dual vector. Okay, so how do we define the pullback of any dual vector omega? Okay, the pullback was defined such that this inner product of the pullback with a vector. Okay, remember both of these. This belongs to TPM. This belongs to TP star M. This was defined as omega time acting on the push forward of V, where these are now at TF of P M and TF of P. Okay, so this was kind of a definition of what we mean by the pullback map. Okay, now instead of talking about the pullback on, and this I can think of as f star omega. I mean, a dual vector can be thought of as acting on a vector. Okay, through this inner product. Similarly, a 0-2 tensor can be thought of as taking in two vectors as input. Okay, and sort of by the and you can construct a basis of them by taking tensor products of things like this. Okay, so you can construct a basis set of these 0-2 tensors. Okay, and so using this property, okay, of dual vectors, you can show that the metric gets pulled back. Okay, the metric acting on the push forwards is equivalent to the pullback of the metric acting on the original vectors. Okay, it really follows from how we define the pullback.
Okay, sir.
Okay, we proved this, but it's just one step further to just prove this more general rule for arbitrary tensors. Arbitrarily 0R tensors. Okay, you can basically show that if I have a 0R tensor omega, omega acting on takes in R tensors, and if I act omega on the push forward of these R tensors, this is the same as the pullback of omega acting on the original R tensors. Okay, this is an inner product. This is an inner product, let's say at f of p, and this you can think of as an inner product at p. Okay, at the original point p. Okay, so now let's just work out this equation. Okay, what is this equation? This equation. Okay, we'll work it out in components. So if we have a particular coordinate chart, okay, so we have some coordinate chart psi here, and we have some other coordinate chart phi here. And this, let's say psi takes us to some coordinates x, psi takes us to some coordinates y. Okay, so the statement that we've introduced for what is an isometry is coordinate independent. Okay, so again, isometries are defined in a coordinate independent way. They're a class of diffeomorphisms which preserve the metric. There's a coordinate independent notion of what it means to preserve the metric. Okay, now what we're saying is now what we're saying is now let's assign coordinates x, y, and let's look at what this equation that f satisfies, what that equation should look like, okay, in a particular coordinate system. So in a particular coordinate system, okay, the right hand side of this equation, okay, is just g mu nu of p, okay, and if I write out the full metric using some basis components, it's dx mu dx nu, where these are dual basis vectors at t in this space. Okay, so this is what I have on the right side, and on the left side, okay, we have the pullback of G. So the pullback of G is G alpha beta, and if you recall what we had done previously, we have this Jacobians. Okay, so this Jacobians allow us to define the pullback. Okay, so it's partial y alpha x alpha, where y alpha are the coordinates of f of p. Okay, partial y beta x nu, G alpha beta f of p is equal to G mu nu p. So y are the coordinates of f of p, x are the coordinates of p. Okay, and you could be using different coordinate charts. Okay, so you could be using either the same coordinate chart psi, okay, in both cases, or you could be using a different coordinate chart phi over here. Okay, you don't have to be using the same coordinate chart after the transformation. Okay. And so what you get is just this is the equation. Okay, this is the equation that we have. Ah, sorry. Okay. That's right. Yes. Okay. You can use different coordinate charts. Okay. And so in coordinates, the metric. So y as a function of x is really implementing that map f. Okay. F takes you from x to y. So in other words, this map y as a function of x. Okay. Strictly speaking, f is not a map from x to y. Right. What you have to do is first invert the first coordinate chart. So this will take you from x to the point P. Then you act with f. This will take you to f of P. Then you act with the map phi, and this will take you to y. So this in shorthand is what we're calling y of x. Okay, and we're saying that, okay, so if we suppress the coordinates, okay, we in shorthand we're saying that y of x is the same as taking f of x. Okay, and in other words, this equation is defining for us, okay, which f's will satisfy, the f's that satisfy this condition, only those f's are isometries. Okay, if I'm given a metric, there are only certain f's or certain coordinate transformations. So not just coordinate transformations, certain diffeomorphisms, which preserve the metric, and they are the ones which satisfy this equation. Okay, now here are some properties of these isometries. Okay, the first one is fairly obvious. That is the identity map. That is, if you take every point on the manifold and you map it back to itself, that's the identity map. This identity map is an isometry. Okay, it's always an isometry for any metric. Okay, that should be fairly obvious. Okay, because in that case, the pullback of the metric will just be the original metric. So this is called the identity map. The second thing is, if you have an isometry f, okay, so there's some isometry through f, then f inverse will also be an isometry. Okay, so the inverse will also be an isometry. Okay, you can show this quite easily with one step. I'm just not going to work it out explicitly. Okay, and in components, it's quite easy to see. Okay, if the Jacobian exists and this is a diffeomorphism, then the inverse Jacobian also exists because it's a diffeomorphism. And therefore, I can invert this equation and take this to the other side. Okay, and then it looks exactly like this original equation. Okay, after inversion, but with p and f of p exchanged, or x and y exchanged, or equivalently, instead of talking about y as a function of x, I'm now talking about x as a function of y. So that's the inverse map. Okay, so f inverse is an isometry. The second thing is, if I have two isometries, f, which preserves the metric, and then another action g, which takes me again to the manifold M. Okay, if f and g are two isometries, then the composition of these isometries, that is the map from those original manifold all the way directly to this last manifold, copy of the manifold here, this is also an isometry. Okay, so this property is called the closure of isometries. That is, the composition of any two isometries is also an isometry. Okay, it preserves the metric. So the set of all isometries, okay, therefore forms a group because it satisfies all the group properties. Okay, this operation. So what is the group? The elements of the group are isometries. Okay, that is, they are diffeomorphisms that preserve the metric. And the group operation is composition of these isometries. Under this composition, you get back an element of the same set. Okay, you get back an isometry. The inverse of every group element exists. That is, there is an f inverse, such that f circle f inverse is the identity. So the first property we started with is that there is an identity operation. Okay, so basically the set of all isometries forms a group. Okay, and this forms a group on a manifold M with a metric G. So you have to be given the manifold and a metric, and given the manifold and the metric, you can find the set of all possible isometries. That set of isometries forms a group. Okay, and just a reminder, what is an isometry? It's a subset of diffeomorphisms that preserves the metric. or preserves the inner product of vectors. Okay, so M manifold plus metric together define this group. And this group is the set of diffeomorphisms restricted. Okay, so you're not taking all possible diffeomorphisms, but a subset of them which preserve the inner product of vectors. Okay, any questions? We'll do a few examples so that this becomes clear.
So,
Yeah.
like we define parallel transport that also preserve the inner product. So is it a kind of isometry or?
Parallel transport preserves the inner product. Yeah, okay, so we'll discuss that. That's a good question. Okay, so what was parallel transport? So when we had a manifold M, okay, with a metric G, we use this to define a connection. Okay, and we said that there's a unique connection gamma, and this unique connection gamma is such that it preserves the inner product of two vectors. Okay. No, sorry. Okay, this gamma is defined such that for any vector field X, okay, if I take if I take the inner product of two vectors, okay, then this is 0. Okay, or in other words, this if I have some vector field X and I have the inner product evaluated here versus the inner product evaluated here. Okay, this inner product is preserved, right? That's what we have defined as the unique affine connection or unique Christoffel symbol, right? In a coordinate dependent way, you talk about the Christoffel symbol. In a coordinate independent way, you talk about the affine connection. So this is a unique connection. Okay, but what is the difference here? The difference is that here the thing that you are taking the inner product of. Okay, this is V1 and V2 at the point P. This is V1 prime and V2 prime at the point F of P. Sorry, let me not call it F of P. This is at and there's a metric G at this point, and there's a metric G prime at this point. Okay, so what we're saying with this equation is something like we parallelly transport V1 to the point P prime. Okay, so we go from P to P prime. We parallelly transport V, okay, using parallel transport to V1 prime. And we parallelly transport V2, okay, again using parallel transport to V2 prime. And we parallelly transport the metric. Okay, we parallelly transport the metric to G prime. Okay, and then the claim is that this inner product is the same as this inner product. Okay, but the important point here is that this this map from P to P prime, this is a path dependent map. Okay, this is path dependent because parallel transport depends on the path that you take in general on a curved space. It depends on the path that you take to get from the original point P to the point P prime. Okay, so as we've seen in curved space, if I go around a sphere, for example, one way, okay, to a point, or if I go around another way to the point, then in a curved space in general, the v prime that I get will not be unique. Okay, there are different ways to get the v prime. Okay, however, for a diffeomorphism, okay, if I have a map F, okay, it doesn't care. I don't have to think about continuous diffeomorphisms to get from one point to another point. I directly have a smooth map which takes me from one point to some other point on the manifold. Just given the existence of such a smooth map, okay, there exists a unique pullback for the metric G. Okay, there is a unique pullback. So there's no dependence on how I arrived at this final manifold. Okay, so there's no path dependence, okay, of this sort of diffeomorphism. So these two things are in general not going to be the same. Okay, the fact that the inner product is preserved. Okay, this tells you what, you know, it defines for you a connection. Okay, it defines for you a connection by which you can follow a rule to get parallel transport. Okay, but this rule for parallel transport in general is path dependent. Okay, for how you transport, along which vector field X am I transporting. Okay, whereas the rule that we have here, okay, for F, for arbitrary diffeomorphisms, okay, this preserves the inner product, but it doesn't care about any particular path that you're taking to get from the original manifold configuration to the new manifold configuration. In fact, when we do an example, I'll show you the difference that you get between parallel transport and and what happens to vectors under this push forward, okay, or what happens to the inner products. Okay, so let's do some examples and then maybe it'll become clear. Okay, so let's take an example of Rn with Euclidean metric, okay, that is delta ij. So so the first thing is the set of isometries, okay, of this space, okay, of Rn with this Euclidean metric is the Euclidean group En. So what is the Euclidean group En? Well, it's a map from, if I assign the usual coordinates on Rn, that is, I assign a vector x where x is x1 through xn. Okay, if I assign this vector of coordinates, then any general transformation, and this is a coordinate patch that covers the entire manifold. Okay, any general transformation x which takes me to Rx plus t of this form. So x1, x2, xn goes to x1 prime, x2 prime, dot 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 xn prime, where R is an n by n matrix. Okay, x1 through x acting on x1 through xn, plus t is a column vector of shifts. Okay, delta 1 through delta n. Okay, so the claim is that this transformation, okay, which you and the other important thing is this R satisfies this property that R transpose R is the identity. Okay, this defines a rotation operation. Okay, which acts like this defines rotation operations. So rotations plus translations, that is constant shifts, okay, in the x, y, or z directions. Rotations plus translations together, they preserve the norm of any two vector fields. Okay, this is the claim. And these are called inhomogeneous rotations. So that is their rotations, but they also allow for translations. Okay, so this set of all possible f. So when I define the set of all possible f, I mean all possible rotations combined with all possible translations. This defines the set of all possible f's. Okay, when I take the set of all possible f's, I am getting the full set of isometries, okay, that are associated with this metric. So the first thing to do is to see that such a transformation indeed is an isometry. That is, it preserves, either you can think of preserving the metric or preserving the inner product of two vectors. Okay, So one thing that I'll mention is that it's not necessary that the determinant of R is +1. Okay, that is, we're allowing for, it's not necessary for F. This is not a necessary condition for F to be an isometry. Determinant of R can be either +1 or -1. Okay, from this condition alone, right, you get, if you take the determinant of both sides, I will get determinant of R squared is 1, which means determinant of R can be +or -1. So you have what are called proper rotations and improper rotations that involve the parity operation. Okay, and both of them are, I mean, all kinds of operations, whether with parity or without parity, those are all what do you call them? Those are all valid isometries. Okay. So R belongs to the set of matrices On, that is orthogonal matrices of rank n, and T belongs to the set of column vectors of Rn. Okay, and the set of R and T together define the transformation, and the set of all possible R's and T's. Okay, this defines for me the group of isometries associated with the Euclidean metric. Okay, and this group is called En. Okay, so let's look at a picture of what exactly is going on. So this is M. This is the manifold M. Okay, M is, in this case, you just an n-dimensional Euclidean space. This is the metric G. We're again mapping to the metric M and the manifold G. Sorry, the manifold M with the metric G. This is the point P, and there in yellow I've shown the vector field X. Okay, so there's a vector at the point P. There's a vector at the point P prime over here, and then there's similarly in magenta there's a vector Y of P. Okay, which is here and over here. And now what we do is we take the map F, okay, which maps us from MG to MG, okay. And what we do is now, instead of taking X at the point F of P, what we do is we consider the push forward of this vector. Okay, the push forward of this vector is F star X of P. And the push forward of this vector is F star Y of P. Okay, and what we want is, so we have a metric at this point. This is the metric at this point, G of F. So we can construct the inner product of XP, YP with the original metric GP. Okay, so that is, we can construct this quantity. Or we can construct this quantity, that is GFP, F star XP, F star YP. And if these two are the same, then we'll say that the map F is an isometry. Okay, that is, this equation is satisfied, F is an isometry. In components, let's write this out in components. Okay, so let's work in a particular coordinate basis. Okay, so xp is x mu p partial x mu, where this derivative is evaluated at xp. Okay, that defines a basis of vectors at the point P. And similarly, yp is some basis coefficients, again expanded in the same basis vector set, partial x mu at the point xp. Okay, so these are vectors at this point. Okay, so don't get confused. You're using the same coordinates x, right? Because you're talking about the same vectors, okay, at the same point P. Okay, so these define the two vectors that I have over here. Now, if I want the push forward, okay, of this XP, I want to push it forward, and now for the first time I'm actually using F. Okay, we see that F induces a map F star, which is unique. Okay, which gives me the push forward map. So the push forward of XP is Jacobian partial y mu partial x nu acting on x multiplied by x nu, okay, where x nu are these components, times partial y mu, where y mu gives me the coordinates of this point F of P. Okay, so y gives me the coordinates here. Okay, and these coordinates may be the same as the original coordinate system that I was using on M, or they might be a new coordinate system. It doesn't matter. Okay, so so we'll write this over here. So this is y, but these are the coordinates of F of P. Okay, that's the important thing. These are the coordinates of F of P in whatever coordinate patch you use. And similarly, we can define the push forward of yp, okay, as Jacobian partial y mu partial x nu, y nu, again partial y mu, y of fp. Okay, so this is the push forward. Okay, and now G of fp, okay, this is the metric at the point fp. Okay, and now the metric at the point fp, we're going to use the same basis that we're using in which we expanded these push forward basis vectors. So we'll use the corresponding dual basis, okay, which is dy mu dy nu, and we'll use the metric at that point. We'll use the metric at this point, okay, which is G of FP. Okay, so this is not a push forward. This is the metric at that point. This is G mu nu of FP. And the original metric G at the point P is of course just G mu nu P dx mu dx nu. Okay, so what we can do is we can use this GFP to take the inner product of these push forward vectors, and we can use GP to take the inner product of the original vectors. Okay, so if we take G of FP acting on the push forward vectors, what we get is GFP acting on F star XP, F star YP is G mu nu at FP times partial Y mu, partial X alpha, partial Y nu, partial X beta, X alpha of P, Y beta of P. Okay, so I just plugged in, okay, this dy mu acting on partial Y mu. I mean, I have to use different indices, but it will set this mu index equal to this index. Okay, so so for all practical purposes, I can basically just get rid of these two. Okay, and just write it as G mu nu FP times partial Y mu, partial X nu times X nu. And similarly, when this acts on this, it will get rid of this and set this index equal to nu. Okay, and then I have to replace this by new dummy index. Okay, so what I'll get is partial Y mu, partial X alpha, partial Y nu, partial X beta. This is X alpha, this is Y beta of P. Okay, so this is just G acting on the push forward vectors. Now, if we want, so this is, if we want this to be an isometry, okay, then you want this to be equal to the original inner product. That is, you want it to be equal to G alpha beta of P acting on X alpha P, Y beta P. So you want these two to be exactly the same. And this inner product should be exactly the same no matter what vector fields X and Y we choose. Okay, which means, in other words, we want this to be equal to this. Okay, so we want these two things to be equal. And now what we'll do is we'll work with the Euclid now, and this statement is true independent of the coordinate charts that we choose. Okay, no matter what coordinate charts that we choose. However, what we can do is we'll choose the standard Euclidean metric in standard Cartesian coordinates, just to see what this looks like in standard Cartesian coordinates. So in standard Cartesian coordinates, we'll choose the standard Cartesian coordinates for X, but we'll also choose the standard Cartesian coordinates for Y. Okay. So in the standard Cartesian coordinates, G mu nu of P is delta mu nu using Euclidean X. And therefore the right hand side of this equation, which is this, is G alpha beta, X alpha P, Y beta P, and this metric is just delta alpha beta, okay, X alpha Y beta, which if I expand in components is X1 Y1 plus X2 Y2 plus dot dot dot. Okay, this is the usual dot product that we have of four vectors, of vectors in n dimensions. Where this X1 is, so the vector X has components X1 through Xn. Okay, and these are all components which are evaluated at the point P. Okay, it's a vector field, so the vector components of the vector change from one point to another on the manifold. Okay, and now what we do is we choose our F in such a way that Y is equal to Rx plus T. Okay, that is, we imagine that we are using the same original coordinate charts on M. That is, if you imagine that this was the point P and you had a coordinate chart psi, okay, which gives us the coordinates X of P. And this is the point F of P, and we use the same original coordinate chart psi. So we get X of F of P, and this is what we're calling Y. Okay, so this X is basically coming from the coordinate chart psi. Okay, and we've chosen a particular set of transformations F. Okay, which set? The set where this transformation is R times X plus T, where this X is the original X that we had over here. Okay. Does this make sense? Any questions at this point? So again, I'll just reiterate, you don't need to use the same coordinate charts here. We are just using the same coordinate charts. Okay. Okay, so if you do this, now you can evaluate the Jacobian of the transformation, which is partial Y mu, partial X alpha. Okay, so what do we mean by this transformation? It means that there's an orthogonal matrix R such that our new coordinates y mu, okay, will be something like this. Okay, where these are constant matrices. Okay, which are coordinate independent matrices. So if I take partial y, partial x alpha, what I'm going to get is just the mu alpha component of R. Okay. That is, I'll get this. So, so now our original x, which was x alpha partial x alpha at P, when I push it forward, okay, what do I get? I get partial y mu partial x alpha times x alpha partial y mu, but this is now at the point f of P. And this, we evaluated this Jacobian, it's just this R mu alpha. So it's R mu alpha x alpha partial y mu f of P. Okay, so this is the push forward of x. Okay, so this is understood as an equation. Okay, but let's try to understand it using pictures. Okay, so let me just use a highlighter. So here's an origin. Okay, and here is a point P. Okay, and this is the vector x at the point P. And now what we have done is we have performed a rotation. Okay, so let's assume we've just performed a rotation. So t is 0. Okay, we just have a rotation. Okay, a rotation is of the point P is rotated to the point f of P. Okay, so this point P is rotated to the point f of P over here by some rotation matrix, which rotates you by an angle theta. Okay, what we want to know is what is the push forward of the vector xp? Okay, what is the push forward of the vector xp? The claim is that if you look at the push forward and the components of the push forward, the components of the push forward are rotated by the same rotation matrix R, okay, by which you use to rotate the point P to the point f of P. Okay, which means that if our xp was pointing this way, if we had parallelly transported xp, okay, we would have got something which is parallel. These two vectors would be parallel. So this would be what you would get if you parallelly transport. This is x parallel of f of P. But instead, the push forward of x, okay, actually rotates x, okay, by the same angle theta. So this x itself gets rotated by the same angle theta. If you think about what a rotation means, okay, imagine that I have yeah, imagine that you have a bunch of vectors, okay, a vector field like this. Okay, now imagine a rotation. Okay, the rotation is not just going to take this point, you know, to some point here, okay, through rotation, but it's, if you imagine rotating, literally imagine turning the paper. Okay, if you literally imagine turning the paper, the vectors are going to rotate as well. Okay, so you have to rotate the vectors as well as rotate the point P so that it lands up at this point f of P. So you not only have to rotate your point P, but you also have to rotate vectors, okay, as you get from this point to this point. Now, when you say rotate, okay, it's a little bit tricky because these vectors live in a different vector space than the original vectors. Okay, so you can't compare this with the original vectors. What you have to compare is with the parallelly transported version of xp. So if instead of, if I went from this point P to some other point f of P, if I had parallelly transported, I would have got something. But if I'm rotating, okay, that is, I'm making a diffeomorphism, then the vectors that I get here will not be in general parallel to the original vector that I started with. Okay, in this case, you see that the vector itself is rotated. Okay, the components of the vector themselves are rotated. And you can compare this push forward with the parallelly transported vector x, okay, x parallel f of P. And you will see that this push forward is rotated relative to the parallelly transported x. Okay. So this f star of xp, okay, which is the push forward, I can think of it as having some components x prime mu f of P, okay, partial y. These components x prime, okay, are related to the original components x of this vector as x prime mu at f, which are coordinates at fp, are equal to r mu alpha x alpha beta. Okay. So, and in general, if I also have a translation, okay, if I have just rotation plus translation, then in components, what we're saying is that x prime mu at the point rx plus t is related to the original components of the vector x at the point x, okay, with but plus a rotation, okay, by this r mu alpha. Okay, or equivalently, if you call this rx plus t as y, okay, what we're saying is x prime mu of y is equal to r mu alpha, x alpha, but now I go from y back to x, that is I use the inverse map, f inverse y, this gives me x. Okay, and the inverse map is basically you first take the negative of translation, so you translate back and then you take the inverse rotation. Okay, and this is the x alpha on this. Okay, the important point is that here we've done this in coordinates, but remember that the original vector x is expanded in a set of basis vectors which are partial x, which are defined at the point P. The new vector, that is the push forward xp, which is here f star xp, this push forward, which is shown in magenta, that push forward is defined using basis vectors partial y, okay, which are basis vectors at the point f of p. Okay, they're not basis vectors at this point p. Okay, but this equation is true in components. Okay, and now if I want to, okay, so the first thing is that this f star xp, okay, this push forward of xp, this is not the same as either the original vector field x at f of p. That is something completely arbitrary, right? The vector, the original. So there is also a vector that we could have drawn here, which is the x at this point. Okay, this is something completely different. Okay, the push forward is neither that vector, nor is it the parallelly transported vector x parallel f of p in general. Okay, in general, this is neither this nor the parallelly transported xp. In general, the parallelly transported x parallel is not even defined in general, right? Because this parallel transport depends on a path. Okay, in general, parallel transport depends on a path, and in Euclidean space, it turns out that it's path independent. You can parallelly transport around any path, and you'll always end up with the same vector. So it's path independent. Okay, but on a general curved space, it does depend on the path you take. Okay, so this is not even well defined in general, because we need to specify a path. The second thing is that this f star xp, okay, if you're in Euclidean space, okay, then this is uniquely defined. Okay, what we mean by parallel transport, and it becomes path independent. Then f star xp is a vector at f of p which has components rotated by theta. Okay, as well. Okay, so the point f of p itself is rotated relative to the point p, but the vector f star xp is rotated relative to what? Okay, it's rotated. I can't really compare with the original xp because these live in different vector spaces. One is the vector space here and one is the vector space here. Okay, but it's rotated by theta relative to the parallelly transported xp, which is x parallel p. Okay, and in general, such a comparison doesn't make sense because x parallel p is not defined. Okay, because parallel transport becomes path dependent. In Euclidean space, all the paths give you the same x parallel of f of p. Okay, so if you want to visualize what's happening in Euclidean space, you imagine this set of vectors, okay, all over the entire space. Imagine the set of vectors. Okay, this is some vector field, okay, on the paper. And now I have a point P with some vector, and I rotate it till it. So this gives me xp, this gives me x of fp. Okay, now what we do is we rotate the paper. Okay, you rotate your paper so that this point P reaches this point f of p. Okay, so it reaches that point f of p. So this will perform a rotation by some angle theta. Okay, you can choose some origin about which to rotate. Okay, so I will make some rotation, and therefore the new vector xp that I get after pushing forward would be when I rotate like this, then this xp also gets rotated. Okay, that becomes f star xp. But how do I tell that this is rotated? Well, I can tell this is rotated by comparing it to the parallelly transported version of this vector, which will look like this. Okay, it's just parallel to the original vector, and I can see that it's rotated by an angle theta. This comparison doesn't make sense in a curved space because there is no natural notion of what it means to parallelly transport the original xp. Okay, that would be a path dependent statement. In Euclidean space, okay, you always end up with a unique x parallel p. No matter which path you choose to transport, you will always end up with the same parallel x parallel p. Therefore, you can make this comparison in Euclidean space, and you will see that the components of your vector are rotated by an angle theta. Okay, that is f star xp is also rotated by an angle theta. Okay, neither of these, this one or this, have anything to do with what the actual vector field x was at the point fp. Okay, is this clear? Any questions here? So is it clear or is it not clear at all? Or if you have something specific, we can go over it again.
It's clear.
What about the others?
It's clear. It's clear.
Okay, so now let's look at the alternative picture. So in this picture, we were thinking about pushing forward the vectors. Okay, let's look at the alternative picture where we pull back the metric. So if we have our original vectors xy, okay, and we have this point P, and then this is the point f of P, and there's a metric at f of P. Now what we want to do is we want to pull back this metric and bring it back to this point. So we get f star g of f of P. And if the pullback metric is the same as the original metric here, okay, this would also preserve the inner product of vectors, okay, of vector fields, and we would call this also this map F would also be an isometry. Okay, in components again, it's easy to understand what's going on. So the inner product can be thought of as G mu nu. Okay, then if I look at the push forward, it's R mu alpha x alpha, R nu beta y beta. Okay, and I want this to be equal to the original inner product, which is G alpha beta x alpha y beta. Now I can think of this R as associated with this X, in which case I'm thinking of this as a push forward. Okay, or I can think of this R as associated with this G for arbitrary vector fields X and Y, and in which case I'm thinking of this as a pullback of the metric. Okay, so if I now associate them with the metric G, and I demand that this equation is satisfied for any X, Y, then for our Euclidean metric, for example, okay, we're saying that if F is an isometry, okay, we have delta mu nu times R mu alpha beta, R nu beta is delta alpha beta. Okay, this is the original metric, but the subtlety is that delta mu nu are the components of the metric, but these are the components of the metric at f of p. These are the components of the metric at p. They just happen to be the same in Cartesian coordinates. Okay, so so we have this kind of equation: delta mu nu R mu alpha R nu beta is equal to delta alpha beta. Or in other words, if R transpose R, okay, if I write this as a matrix, R transpose R is the identity matrix. Okay, so for this special class of transformations where R is a rotation, you would indeed find that you have an isometry, okay, for your Euclidean metric. Okay, so this justifies what we had said earlier, which is that rotations plus translations, okay, this forms the set of isometries in n-dimensional Euclidean space. Where did we say that? Yeah, rotations and translations together, this form the set of isometries in n-dimensional Euclidean space. Okay, a similar example which is related is if M is Rn. Okay, this is now coming closer to special relativity. And if your metric is Minkowski, okay, so if your metric in standard Cartesian coordinates is eta mu nu, then in general, the claim is that the set of isometries associated with this metric are the point x gets taken to the point lambda x plus t. Okay, where now, just like we had this equation here, R transpose R on delta is equal to delta. Okay, you can check that you would get something like lambda transpose G lambda is equal to G, where this G is at f of p, this G is at p, but in components, this is the same eta, this is the same eta. Okay, and again, the translations T belong to Rn. Okay, these are arbitrary translations both in space and time. So this set of transformations, okay, the set of transformations like this, which are specified by a choice of lambda and a choice of t, where lambda satisfies this equation. Okay, you might recognize this as the set of matrices O3, 1. Okay, the set of orthogonal matrices with metric signature 3, 1. This is the set of inhomogeneous Lorentz transformations. Okay, and this set of inhomogeneous Lorentz transformations, that is Lorentz transformations lambda belonging to O3, 1 and column vectors T belonging to Rn. If I take the combined set of all possible lambdas and T's, that defines for me something called the inhomogeneous Lorentz transformations, or equivalently it's called the Poincare group. Okay, this gives all possible isometries of the manifold M. In this case, the manifold M is Rn. Okay, so Minkowski space has the isometries of the Poincare group. Okay, the set of isometries forms a group called the Poincare group. And so one important point is that in general, any smooth one-to-one map, okay, between the manifold to itself is a diffeomorphism. That is, if I find some y as a function of x, possibly nonlinear functions, okay, as long as these are smooth one-to-one functions, that is infinitely differentiable, then all of these are diffeomorphisms. But only a restricted set of these diffeomorphisms are isometries. Okay, these are the set of diffeomorphisms which preserve the metric G, or which preserve the inner product between arbitrary vector fields. And the other point is that diffeomorphisms and isometries, these are coordinate independent notions. Okay, whether something is an isometry or whether something is a diffeomorphism, this has nothing to do with any particular coordinate system that you're using. You can use any coordinate system. You can use a certain coordinate system before you start your transformation. You can use a different coordinate system after you enter your transformation. Still, the notion of the isometry doesn't care about those coordinates that you're using. It just cares about the map F, which is taking you from the manifold back to itself. Okay. Okay, any questions at this point? Okay. So now we come to a related concept, okay, which we've discussed in the GR class, which is the idea of killing vector fields. Okay, and now we have all the tools to really understand in detail what really a killing vector field means. So suppose I have a manifold M with metric G, and a copy of this manifold with M with metric G. And now suppose we have a vector field X. Okay, this is some vector field that lives on this manifold. So we've seen in the previous classes that if you have a vector field X on a manifold, then this vector field X generates a flow. Okay, or it generates a one parameter family of diffeomorphisms, which we call sigma t. Okay, where sigma t, if you take your original transformation, we define the sigma t X. Okay, if we take all possible starting points for the flow on the manifold, so we leave this as an open slot. Okay, then the sigma t is a map. Sigma t is a map from the manifold back to itself. Okay, and sigma t in coordinates takes the coordinate point at coordinate x and it maps it to the point e raised to tx. So t is like the time, the amount of flow that you had. Okay, it's a parameter associated with this flow. And infinitesimally, we've seen that this flow is x. The coordinates x mu go to x mu plus t times capital X mu, where X mu are the components of this vector field. Okay, evaluated at X. So we've seen that if you have a vector field, it generates a flow, and this generates a one parameter family of diffeomorphisms. Okay, so let's choose some infinitesimal transformation, sigma epsilon. Okay, so T is epsilon. Sigma epsilon defines a diffeomorphism. And now we ask, okay, is this diffeomorphism, is it also an isometry? Okay, is this diffeomorphism an isometry? Where did this diffeomorphism come from? This diffeomorphism came from having a vector field X, okay, on the manifold. Now, this is so whether it generates a flow has nothing to do with whether there's a metric on the manifold. This X will generate a flow, and it therefore generates a diffeomorphism. Now we're asking a new question, which is now that we have a metric on the manifold, will this flow or will this diffeomorphism that is generated by X, will it preserve the metric or will it preserve the inner product of arbitrary vector fields? Okay. If it does, then we say that X is a killing vector field. Okay, so let's go over that more slowly. So if this diffeomorphism, okay, the sigma epsilon, it generates a pullback map, a unique pullback map on G. Okay, and this pullback is, so this is the point P. After diffeomorphism, it becomes sigma epsilon P. There is a metric G at this point, sigma epsilon P. I pull it back using the sigma epsilon star P map. Okay, there's a unique map for the pullback. So I pull back this G sigma epsilon P. So that is sigma epsilon star P acting on G sigma epsilon P. That is the left hand side of this equation. If this is equal to the original metric that I started with here, okay, then we say that the transformation sigma epsilon is a is an isometry. It preserves the metric. And since the sigma epsilon was an infinitesimal flow generated by the vector field X, X is then therefore called a killing vector field. That's just a name given to this vector field X. Okay. Now we show this for infinitesimal transformations, but this will automatically be true for any finite transformation by some finite parameter T, because the finite parameter can be thought of as applying a series of successive infinitesimal transformations to build up to the big flow. Okay, rather than going to an infinitesimally nearby point, we keep making a series of infinitesimally nearby points till we flow from here to here. Okay, and therefore the diffeomorphism which is generated by this large flow by some parameter T, okay, this finite transformation also gives you a gives you an isometry. Okay, it preserves the metric. Okay, this will automatically happen if it happens for infinitesimal transformations. Okay, now this condition that we had, that is the pullback of the metric G, okay, is equal to the original G. This is equivalent to the statement that the Lie derivative of G, where the Lie derivative is taken along X, this is 0. Okay, this is the definition of what we call the Lie derivative. Okay, by definition, we are comparing G with being pulled back with the original metric. The difference between those two, okay, the difference between these two things, the left hand side and the right hand side of this equation, the difference between this and this, okay, we define the Lie derivative as the difference between those two divided by epsilon in the limit epsilon goes to 0. Okay, this limit epsilon goes to 0. This is what we call the Lie derivative of G along X. So if the Lie derivative is 0 everywhere in the manifold, then we say that that X is a killing vector field. Okay, so this equation defines something called the killing equation. So it's quite elegant, right, and very simple to understand now. If the Lie derivative, if X is a vector field such that the Lie derivative of G is 0, okay, then and remember the Lie derivative of X acting on G is so Lie derivative acting on any tensor T produces a tensor of the same type, okay, as T. So so if this tensor is 0, okay, what we're basically saying is that X is a killing vector field, or the diffeomorphisms generated by the flow induced by X, those diffeomorphisms preserve the metric. Okay. So we can write down quite easily now in components what this equation is. We had written it down earlier, right? So if you have a 0-2 tensor, the first thing is just you differentiate G. So you write X alpha partial alpha G mu nu. But then the other components of this tensor would be you replace one of the indices of G with a dummy index and you differentiate the X coefficients, okay, with an alpha. Since all of these are lower indices, you will only get plus signs over here when you perform this differentiation. So plus partial nu X alpha G mu alpha is equal to 0. If you had a mixed tensor with some upper indices and some lower indices, recall that you would have some minus signs here and the way you replace the indices is a little bit different. Okay. The repeat, I mean the index that you pull out will be on X rather than on the derivative. All right. Anyway, so this is the killing equation. This is basically just this equation expressed in a particular coordinate basis. Okay. And we see, I mean, I'd written this before during the regular GR class. So if a vector field X satisfies this killing equation, then the local geometry, that is the inner products of vectors, it does not change when you flow along X. And alternatively, we can show that the killing equation can be written by using the unique torsion-free connection, that is your Christoffel symbol gamma. You can show that, again, this is an exercise, you can show that this equation can be written in the form del mu x nu plus del nu x mu is 0, where this del depends on the Christoffel symbols, which depends on the metric. Okay, and alternatively, this can be written using explicitly the Christoffel symbol like this. Okay. Okay, I'm not going over this and I'm going over it a bit fast because we've already seen this before. Okay. And now if you have a set of killing vector fields, okay, x1 through xn on the manifold M, okay, with the metric G, then this set of killing vector fields, okay, is called linearly dependent if there exists non-zero coefficients C1 through Cn such that C1 x1 plus dot 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 plus Cn xn is equal to 0. That is, you get a zero vector field by adding up, by taking some linear combination of these. Then you say that this set is linearly dependent. Okay, otherwise it's called linearly independent. And on a general n-dimensional manifold with M with the metric G, there can be any number of linearly independent killing vector fields in general, okay, depending on what the metric is. However, there turns out to be a maximum number of linearly independent killing vector fields. Okay, and there are special metrics G, okay, which are referred to as maximally symmetric spaces. So I have a manifold, but I put certain special metrics on it. Okay, for example, R2 with the Euclidean metric is one of those special metrics, in which case you obtain the maximum number of possible linearly independent killing vector fields. Okay, and this maximum number of independent killing vector fields turned out to be n into n plus 1 by 2. Okay, not proving this, I'm just stating this without proof. Okay, so for an n-dimensional manifold, this is the maximal set of killing vectors that you can have. This maximal set is only realized for some special metrics. It's not realized for arbitrary metrics will have less symmetry or less isometries. Okay, so it has to be a very symmetric type of metric, which gives you this maximal number of killing vectors. And okay, so some other properties. So if xy are two killing vector fields, that means that lxg is 0, lyg is 0. Okay, this is by definition of what a killing vector field is. Then there are two statements which are also true. It turns out that ax plus by is also a killing vector field. That is, if I take linear combinations where a, b are constants belonging to real numbers, if I take a linear combination of two killing vector fields, that also is a killing vector field. Okay, that is L Lie derivative with respect to ax plus by on g. Okay, this by the linearity of the Lie derivative is alxg plus blyg. Okay, and therefore, since this is 0 and this is 0, this whole thing is 0. Therefore, ax plus by is also a killing vector field. The second thing is the Lie bracket of xy. This is also a killing vector field. Okay, that is, we want to show that Lie bracket of xy on G is 0. But you can use the identity that we didn't derive, but I told you about in the last class. The Lie bracket of xy on G is Lx Lyg minus Ly Lxg. And since Lyg is 0 and Lxg is 0, this is 0. Okay, so therefore the Lie bracket of xy is also a killing vector field. So now the set of all killing vector fields. Okay, so that is, I take a killing vector field x1, I take another killing vector field x2, and imagine that take the full set of them. Okay, the full set is infinite dimensional, but it forms a linear vector space. Okay, that is, any linear combination of them belongs to the same space. Okay, and there is a Lie bracket operation on any two of these. So if I take any two of them, the Lie bracket of any two can again be expressed as a linear combination of all of them. So it's some combination of coefficients times xk's. Okay, so these coefficients are called structure constants. And the Lie bracket, as we've seen, satisfies this Jacobi identity, that is Lie bracket of xi, xj, xk. Okay, if I take any three killing vector fields xi, xj, xk, and I take xi, xj Lie bracket with further Lie bracket, so this belongs to the same space, and I take the Lie bracket of that with xk, that again belongs to the same space. And if I sum over these cyclically with ijk cyclically permuted, then that is 0. Okay, that's just an identity of the Lie bracket. Okay, so there's a vector space of these killing vector fields. There's a Lie bracket which is defined on them, which satisfies these two properties. Okay, that this Lie bracket belongs to this space. In general, it's not necessarily true, right? If I take two vector fields xy, okay, then I will get a third vector field. There's no doubt about that. I get a third vector field. But the fact that it belongs to the same restricted space, that's the interesting thing, that it belongs to the set of killing vector fields. Okay, and now what you can do is this entire vector space, okay, which is infinite dimensional, but it now has a finite basis. Okay, you can pick a linearly independent basis for this vector space. And these basis killing vector fields are called the generators of isometries. Okay, so you pick a set of basis killing vector fields. So let's do an example. Okay, so in R2 with the Euclidean metric, there are three killing vector fields. One is translations in the x direction, one is the generator of translations in the y direction, and one is the generator of rotations. Okay, so there are two translations and one rotation. These are vector fields, but you can think of them as generating diffeomorphisms. Okay, by taking large transformations. So Tx, for example, we've seen is a vector field that looks like this. It generates a flow in the x direction, which will generate a translation. Similarly, Ty will generate a flow or a translation in the y direction. And this vector field, which we call Jz, okay, generates rotations. And this generates rotations in the xy plane. This in the xy plane, this will generate some kind of rotations. And you can ask, what is the Lie bracket of any two of them? So you can work out these Lie brackets. Okay, so you can work out Tx, Ty, you'll find that that's 0. You can work out Jz, Tx, and you'll find that Lie bracket, you work it out in components, but you'll find that that's equal to minus Ty. You can work out Jz, Ty, and you'll find that that is equal to Tx. So this Lie, you always get back something in the same space of killing vector fields. So it belongs to the same linear combinations of these three vector fields. So this group or this Lie algebra is called the Lie algebra of E2. Okay, that is two-dimensional Euclidean transformations. And again, any linear combination of Tx, Ty, and Jz. This is also a killing vector field. This will also be a killing vector field. Any linear combination of them is also a killing vector field. Okay, so under a general diffeomorphism, okay, so let me, instead of taking A, B, C, let me take parameters, which are real numbers, which I'll denote as delta x, delta y. This is delta x is some real number, delta y is some real number, and theta is a real number. Okay, so I'll write a general transformation under diffeomorphism. X transforms to the point y, where this is exponential of this killing vector. Okay, with, let's say, parameter t is equal to 1. Okay, so I take this killing vector and I multiply it by 1. Okay, and that generates for me a flow. Okay, so this I can think of as some operation which depends on delta x, delta y, and theta acting on x. Okay, so this choice of delta x, delta y, and theta specifies the killing vector that I'm talking about. Okay, alternatively, instead of doing this as a one-shot killing vector, I can think about doing a series of transformations, first by performing a rotation, then by performing a translation in the y direction, then by performing a translation in the x direction. So this is a different transformation on x, which is O prime on delta using delta x, delta y, and theta. In general, these two transformations are not the same. Okay, these are different transformations. Okay, these transformations will not be the same. This O prime will not be the same as this O. Okay, and if I want to relate these two transformations, I have to use something called the Baker-Campbell-Hausdorff formula. This is similar to what you would have seen in quantum mechanics. If I take e raised to a, e raised to b, this a and b are operators, because remember that this tx is an operator. It's partial x. This is also an operator. This jz is also an operator. It's expanded in terms of partial x and partial y. So, so these are operators. And what I want to do is, if I want to combine two operations like this, e raised to a, e raised to b, to write it as some e raised to something, okay, what I have to do is I have to use this BCH formula where I write it as e raised to a plus b plus half Lie bracket of ab plus 1/12, then some more complicated Lie brackets. Okay, but the important point is that after the dust settles, when I evaluate all these Lie brackets, at the end of it, I get back something in the killing vector space. So at the end, whatever I get, okay, it's going to be a horrible mess, but at the end, whatever I get can always be expressed, okay, using a linear combination of the original killing vector fields. Okay, so it can always be expressed as something like this. So there is always some way to kind of multiply these out and get something that looks like this. Okay, where these delta x, delta y, and theta will be something else. Okay, they'll be different from this delta x, delta y, and theta. Okay. Maybe I should put primes here. Okay, so there is some delta x, delta y, and theta, which can be expressed in terms of these delta x prime, delta y prime, and theta prime, some nonlinear function of those. Okay, so let's imagine that we're trying to do this transformation. Okay, so we take y prime, okay, which is e raised to delta x tx, e raised to delta y ty, e raised to theta jz x. Okay, so this is our operation using the second technique. Okay, using this kind of technique. And now what we can do is we can first ask what happens when we do e raised to theta jz acting on x. Okay, we've seen that before in a previous class. So we take this vector field jz and we do e raised to theta jz, okay, acting on x. And what we've seen is that this is the vector field jz. This is going to generate rotations, okay, as a flow. So this e raised to jz will give me a rotation matrix acting on x. So e raised to jz x times theta will give me some rotation matrix which depends on theta acting on x. Okay, and then I have to act with a translation in the y direction and translation in the x direction. One important thing is that when you're doing these series of transformations like this, rather than doing a one-shot transformation, is that this ty, remember that these are tangent vectors, but they're evaluated at a particular point, right? You're expanding in some basis, but at which point should you evaluate these tangent vectors? Well, the point is that after I perform this, okay, I'm no longer at the point x, I'm at some point x prime. So these tangent vectors have to be evaluated at that x prime. And now again, once again, when I perform the transformation, this tangent or these killing vectors have to be evaluated at the point x double prime, where x double prime corresponds to whatever new point I'm at. Okay. So now if we're now at the point Rx, okay, and then we want to translate. What we'll do is we'll generate a translation Rx plus t, where t is something like delta x delta y. Okay, you can check this later. So, and how did we get this x prime? So if you remember, I'm just exponentiating e raised to gz theta. Okay, so this is the operator acting on x. What you will get is x cos theta minus y sin theta. Similarly, if you did this for y prime, okay, and you expanded this operator, we did this in a previous class, so I'm not repeating it. You will get x sin theta plus y cos theta. So x prime, y prime it'll turn out that after the dust settles, when you do this complicated operation on x, you will get a matrix R acting on xy, which is cos theta sin theta minus sin theta cos theta acting on xy. Okay, so this was a simple example of R2 with the Euclidean metric. Any questions here?
Sir, why these commutation relations are always closed? I mean, why we get another killing vector when you commute two killing vector?
Yeah, we proved this. If xy are killing vectors, then the commutator, not the commutator, the Lie bracket of xy. Okay, the Lie bracket of xy acting on G is also 0. We proved this. Therefore, Lie bracket is also a killing vector. Okay. All right. So you can also do this for Minkowski space. Okay. Again, you'll have a set of operations which are translations. So I'll put a label in brackets. So this is a killing vector field. This is not the index of the killing vector field, but rather the new tells me which killing vector field I'm talking about. Okay. So nu is equal to 0 corresponds to translation in the time direction. Nu is equal to 1 corresponds to translations in space. Nu in x direction. Nu is 2 is in y. Nu is 3 is in the z direction. Okay. So this is I can write as delta mu nu partial x mu. These are translations. Okay, so this is basically if nu is equal to 0, then this is non-zero only if mu is equal to nu. That is if mu is equal to 0. So basically t0 will be partial t, partial x0, which is partial t. Okay, so this is translations in time, and similarly the other ones will correspond to translations in space. And similarly, you can write down a set of for j is equal to 1 to 3. Okay, you can write down a set of killing vectors which generate rotations, which I can write as epsilon jmn xn partial xm. Okay, I'm going to go over this a bit quickly. Maybe I can give this as a homework exercise. Okay, you can try to work it out yourself. Okay, it's also there in Nakahara, so you can try to work it out. Okay, but maybe I can give a sharp question which you can actually try out, and it's really worth doing this. Okay. So epsilon gmn xn partial xm, but this epsilon gmn is your usual 3D Levi-Civita symbol. Okay. And then you can also define these scaling vector fields kk, okay, where k is equal to 1 to 3, which are xk partial x0 minus delta km x0 partial xm. So these indices k only run over 1 to 3. Okay, so the Latin indices j only run over 1 through 3, versus Greek indices like mu and nu, they run over indices 0 to 3. Okay, so so you have 3. So how many killing vectors do you have? Okay, you have 4 plus 3 plus 3. Okay, and in general, if you are in n dimensions, this is n minus 1, this is n minus 1. No, sorry. This is not right. Okay, so it's not n minus 1, n minus 1. I'll tell you what it is in a moment. Okay, so so e raised to theta jz, okay, acting on x is r theta acting on x, which is, it turns out, is just this matrix. Okay, so again, just by the similar operation that we did in 2 dimensions, in 4 dimensions, you can show that this rotation about the z-axis would generate a rotation about the z-axis as you would expect. Okay, so I can write this matrix also as an exponential of a matrix, which I'll call jz twiddle. Jz twiddle is just a matrix. Okay, it's some matrix which looks like this. Jz is an operator. Okay, this is something like minus y partial partial x plus x partial partial y. Okay, so there's a difference between an operator and a matrix. Okay, as far as the action on x is concerned, both of these act the same way. If I think of x as a column vector, both of these act in the same way. But this operator is the more general object. Okay, this operator is the more general object because this operation can be defined on arbitrary functions f of x. Okay, whereas this jz twiddle, this matrix of generators, okay, this acts of rotations, this generator of rotations, this can only be defined by its action on t, x, y, z. But this operation of jz, which is this operator, this is more general. It can be defined not just on x, but it can be defined on any f of x. What it will do is it will take me to f of, if f is a smooth function, it will take me to f of x prime, where x prime is the rotated version of x. Okay. So sometimes in the literature, you'll see that, this jz twiddle is called the generator of a rotation. Okay, but you should understand that this is in a very limited context. Okay, that you can think of this as the generator of rotations. Okay, because this is rotating a single column vector like this. Okay, but the more general operation of rotations is performed using this rotation operator. Okay, similarly, you can do this for boosts. Okay, you can take e raised to eta kz, where kz was the thing we had written above. Okay, again, it's an operator because it has to be expanded in a basis of vectors or vector fields. Where did it go? Yeah, k is these. Okay, and you can show that again. Okay, this you can, supposing I take a boost along the z direction. Okay, what I would get is some matrix like this: cos theta, sin theta, sin theta, cos theta. You can show by plugging in that operator here and its action on x and expanding it out. Okay, that you would end up with something like this. Okay, you have to sum up a bunch of terms to show that you get cos and sin. And this again can be written as e raised to eta kz twiddle, where kz twiddle is just an ordinary matrix like this, and no operators. Okay. And the reason is that this kz or the j, right, basically they have things like this. So every time you differentiate a coordinate, you reintroduce a coordinate. So the dimensions of this coordinate stay the same, okay, under this operation. And therefore, it's just going to be a linear combination of the original x's, which is why you can use a matrix over here. Okay, for this case equivalent. Okay, so now in n-dimensional Minkowski space, if you're not in 4 dimensions, in 4 dimensions, you have 4 translations, 3 rotations, 3 boosts, so a total of 10 transformations. Okay, 10 basis scaling vectors fields, translations, rotations. But in n dimensions, it turns out that you have NC2 rotations. Okay, why NC2 rotations? Well, in n dimensions, NC2 rotations plus boosts. Okay, so a boost can be thought of as a rotation in the time, a boost in the, let's say, x direction can be thought of as some kind of effective rotation in the tx direction. Okay, or if it's a boost in the y direction, it's in ty, tz, and so on. So therefore, the number of boosts, okay, is I choose the time coordinate and I choose any one of my other spatial coordinates. Whereas the number of rotations is in n dimensions. You don't think of rotations about an axis, but you really think about rotations in a plane. So I have a rotation in the xy plane, the yz plane. So this is what I think of as a rotation about the z-axis. This is what I think of as a rotation about the x-axis. And similarly, zx is a rotation about the y-axis. But in higher dimensions, a rotation in the xw plane cannot be thought of as a rotation about any axis. And so this mapping from rotation planes to rotation axis doesn't work in higher dimensions. Okay, so so it's only in 3 dimensions that this works. And so in general, the combination of rotations and boosts requires that I pick any 2 coordinates. Okay, if it's a boost, one of them is a time coordinate, one is something else. And if it's a rotation, it's one is an x coordinate and one is a y coordinate, but they have to be different. Okay, so there are NC2 possible ways of picking planes in or hyperplanes in this space of t, x, y, z, and so on. So what I have is n translations plus NC2 rotations plus boosts. So I have n plus NC2 killing vector fields, which is n into n plus 1 by 2 killing vector fields. Okay, these are the number of linearly independent killing vector fields. These form a basis for the space of killing vector fields. Any combination of them is also a killing vector field. Okay, and it's possible to define using this notation of planes. You can talk about the rotation and boost generators using J mu nu. Okay, where mu nu specifies which plane. So if mu is 0, nu is, let's say, x. Okay, or x, nu is equal to 1, then this is a boost. This is a generator of boost in the x direction, or a killing vector field associated with boost in the x direction. If mu is equal to 1, nu is equal to 2, this is a rotation in the 1-2 plane, or in xy. Okay, and I can define this such that if both coordinates are this mu nu indices are Latin indices, okay, ij, then I'll define it in terms of my rotation operators. Okay, in 3 dimensions I would define it like this. And if they are, if one of them is a 0 index, which is a time index, and the other nu is a space-like index, then I define it to be a boost. Okay, this is of course only valid in 4D. Okay, and you can, again, you can count and you'll see that you have only 10 generators. But now I've expressed my rotations and boosts using some common object, okay, which is this J mu nu. And it turns out that this same number of generators, n into n plus 1 by 2, this is realized in Minkowski space, okay, which is flat space-time with 0 curvature. But it's also realized in ADS-n, okay, which is n-dimensional ADS space, and it's also realized in de Sitter space. These are called maximally symmetric spaces. They have the maximal number of possible linearly independent killing vector fields. It turns out that if you calculate the curvature, this has a constant curvature, this has a constant curvature. Minkowski space also has constant curvature. Every point in the manifold has constant curvature. It's just that it has 0 curvature. DSN has positive curvature, ADSN has negative constant curvature. Okay. Okay, and finally, in Minkowski space, the algebra of these killing vector fields, okay, forms what is called the Poincare algebra. Okay, that is, if I take 2 translation operators, they commute. Sorry, their Lie bracket is 0. If I take any of these rotation/boost operators, boost killing vector fields, and I take its Lie bracket with a translation, I would get something like this. The signs might be wrong. I mean, there might be an overall factor missing. Let's not worry about it. Okay, so you get something like this. And if I take the killing vector fields corresponding to rotation/boost again, and I take the Lie bracket of those, I get back a linear combination again of some rotations and boosts. Okay, and you can see again that this algebra is closed. Okay, and just check the overall factors. Again, maybe I'll give this as a homework exercise. Okay, so this Lie algebra defines the so-called Poincare algebra. Okay, the algebra of these 10 basis killing vector fields defines the Poincare algebra. If you want to study this in more detail, okay, we'll cover it in the group theory class, which will be offered next semester. I mean, probably the only difference will be in the group theory class, we won't build up this language of manifolds and so on. Okay, but certainly the Lie algebra of the Poincare group, or the Poincare algebra, will be discussed. Okay, and the final example that I'll give is if you have S2 with the usual metric. Okay, so ds square is d theta square plus sine square theta d phi square. You can solve the killing equation to find these 3 killing vector fields. I believe you might have done that in an assignment already. Lx, Ly, Lz look like this in the standard polar coordinates. And you can show that they satisfy this Lie algebra. Li, Lj is epsilon ij k Lk. In the usual sense, the Lx, Ly commutator, for example, is equal to Lz. Okay, and so on under cyclic permutations. So this defines the SO3 Lie algebra, which is associated with rotations in 3 dimensions. Why rotations in 3 dimensions? Well, if you think about the sphere embedded in higher dimensional R3, there are killing vector fields associated with the isometries of R3. R3 is a bigger space, right? This is only S2 is a 2-dimensional space. R3 is three-dimensional Euclidean space, which has 3 into 3 plus 1 by 2, which is equal to 6 Killing vectors, basis Killing vector fields. Okay, what are those Killing vector fields? There are 3 translations and 3 rotations. Okay, on S2, on this S2, which is embedded inside this R3, some of these Killing vector fields survive because this is isometrically embedded. Okay, some of these Killing vector fields survive as isometries of S2. Basically, the 3 rotations survive as isometries of S2. Okay, the 3 rotations. Translations do not survive as isometries on this S2. So these 3 rotations, which are generated by this, okay, so these are restricted now to, sorry, these are now restricted to the Killing vector fields in R3, but restricted to the surface of the sphere. Okay, so I restrict to the surface of the sphere, and those 3 rotations are generated by these Killing vector fields. Okay, so this S2 is a maximally symmetric space. Okay, and I could imagine that I squash this S2. Okay, why is it maximally symmetric? Because if I have 3 generators, but this is a 2-dimensional space, the maximum number of generators in a 2-dimensional space is 2 into 2 plus 1 by 2, which is 3. Okay, so this has the maximum number of Killing vector fields. So not just R2. Okay, R2 had 2 translations plus 1 rotation. S2 is also a 2-dimensional manifold, but it has 3 quote-unquote rotations. You don't have to worry about whether I think of them as rotations or translations. What I care about is the Lie algebra, okay, of these Killing vector fields. Okay, that's what defines the unique algebra of these Killing vector fields. Okay, so S2 has 3 rotations, but really, if I really want to think about them as rotations, these are rotations in a higher dimensional space. Okay, through the embedding. Okay. Okay, so this S2 is also maximally symmetric space. It turns out that H2, okay, there's a hyperbolic space, which you had worked out in several examples, that is also maximally symmetric space. This is a maximally symmetric space of positive curvature. This is a maximally symmetric space of negative curvature. Okay. All right, and finally, yeah, and if you squash this S2, so supposing I imagine squashing this, okay, so imagine like an orange and you squeeze it, then you'll only have one symmetry direction left, okay, which is in the Z direction. So only LZ will survive as a symmetry generator in that case. Okay, and in general, if I take an n-dimensional sphere, Sn, it has the Lie algebra SO n plus 1, okay, which you can think of as the rotations inherited from embedding this in n plus 1 dimensions. Okay, final thing that I'll just state for today. So not all isometries of the metric G can be found from Killing vectors. Okay, this is a very important point. So isometries are just diffeomorphisms F which preserve the metric G. There is a class of isomorphisms which can be found from Killing vector fields. Okay, which is almost all the isomorphisms we think of, they can be found from Killing vector fields. But the important point is that the isomorphisms that can be built up from Killing vector fields are those which can be built up through infinitesimal flows. That is, I can apply a series of infinitesimal flows to get those diffeomorphisms. Okay, so these diffeomorphisms are what are called continuously connected to identity, right? If my parameter t is 0, that's the identity transformation. As I increase the parameter t, I'm increasing my flow, so I'm continuously changing t, and I'm therefore continuously connected to the identity operation. Okay. So Killing vector fields generate flows which are diffeomorphisms, which are continuously connected to the identity diffeomorphism. But you can give examples of isometries or diffeomorphisms which are not continuously connected to the identity. Okay, for example, in Rn with the Euclidean metric, okay, with n odd, you have these parity transformations, x goes to minus x. These are isometries. Okay, they preserve the metric, but they're not generated by Killing vector field. There's no smooth way in which you can go from all the x's go to minus x. Okay, there's no smooth way to make that transformation. There's no continuous way to make that transformation. Okay, so there's no Killing vector field which will give you this transformation. So these are called discrete isometries. Okay, so parity, time reversal, these kind of things are discrete isometries which you cannot get from Killing vector fields. continuous transformations, continuous isometries, they can be found from killing vector fields. Okay, so that's all I had for today. Any questions?
Sir, is the Lie algebra of ADSN space is also SO n plus 1?
No, it's not. Maybe we'll discuss ADS and DS space and see what their Lie algebras are.
Okay.
At some later point.
Sir, one more thing, like while defining, like while you mentioning the properties of isometries that they form a group, you didn't discuss about associativity. So that holds.
Associativity. Oh yeah, good point. So if I have a group in general, I want these operations, right? Composition like this. This should be the same as G circle F circle H. This is obviously trivially satisfied for, right? It doesn't matter the order in which I compose for diffeomorphisms. Okay, so G circle F circle H will, sorry, maybe it's the other way around. I want H F G. Okay, so I can first do this and then this, or I can first do this and then use this combined operation to give me this. These are all smooth invertible one-to-one maps, so so this is going to be trivially satisfied. Right, there's a unique image for every point P in this final place. Right, so there's a unique final point that I'll end up at always. Given H, F, and G.
Okay, sir.
Yeah, I just want to, that question that Pravesh asked was actually important. So here is O, here is P, and this is vector field V, okay, at P. And this is the point F of P after rotation. Okay, so I perform some operation. Okay, this was a diffeomorphism, okay, by some F. And we saw two things, right? One is we saw that you can take the push forward of V, so which is some F star. Okay, and basically demand that if I take the metric G at F of P, okay, then if I have two different vector fields, V and W, then the push forward, basically the inner product of these two under this GFP, that should match the inner product of WP and VP under with this metric GP. Okay, this is how we defined isometry. So F is an isometry if this is true. Now what we saw is that if, for example, F is a rotation, okay, in two-dimensional Euclidean space, then this vector, so we're not only rotating the point P to F of P, but we're also rotating the components of the vector V. When we go to F star V, the components of F star V are rotated relative to the parallel transported V. Okay, so if I parallelly transport this V from P to F of P, I would get something like this. Okay, this is parallelly transported from here to here. Okay, so this is VP parallel. And if I parallelly transported this omega P, I would get something like this. Okay, now what the claim is that this f star v is also rotated by the same angle theta that I used to perform this rotation. And f star w is also rotated by the same angle theta. Actually, f star w I should probably draw it then over here. Okay, so this angle between them, alpha, that angle will be preserved. Okay, and the norms of these vectors will be preserved. Okay, now what we said is that we insist that this, okay, that this we demanded that this inner product is preserved, okay, of these two vectors using this metric. In the parallel transport argument, okay, we argued that if we want, we choose a connection such that this inner product, okay, is preserved, okay, of these two. In the case of a rotation, okay, in this rotation operation in 2 dimensions, you can see that this inner product is the same as this, and this inner product is the same as this, but this vector is not the same as this vector. Okay, this vector is not the same as this vector, although the inner products are the same. Okay, what's the difference between this set of vectors, which are the push forwards, and this parallelly transported set? Well, the push forwards are rotated by an additional angle theta. Okay, but the inner products are still preserved. So basically, the fact that this inner product is preserved is the condition that GVW, okay, along some path. Okay, I've not specified which path, but whatever path it took me to get here, this is 0. And this is the condition that lead derivative of G is 0. Okay. So they look very similar, but again, this condition itself, okay, depends on the path or the vector field X that you used to get from here to here. Because under a different path, okay, you would get different vectors here. Okay, so the inner product of those two vectors would be preserved for any metric compatible connection. But there is no unique definition of what you mean by VP parallel and WP parallel after parallel transport on a general curved manifold. In Euclidean space, it is unique. In non-Euclidean space, parallel transport is not unique, it's path dependent. Okay, so there is no unique definition of these two, although the inner product will be preserved no matter which path you choose. Whereas with diffeomorphisms, okay, diffeomorphisms F, which are isometries, there is a unique choice of what these two vectors are. Okay, but they can only be compared with vectors at the same point. Okay, so they can only be compared with vectors here. They cannot be compared with vectors here. So if I want to compare them with, you know, the original vectors, the only way I could have done that is by parallelly transporting and then comparing. In general, that parallel transport is path dependent. Okay, so that comparison does not exist. Okay, in general. However, the inner product of these two is the same as the inner product of these two. Okay, does that make sense?
Sir, when uh, mm, it's clear, but one question is that when it like when you say the isometries, it is really related to metric or the space which we are describing from the particular metric. I mean, the isometries like in particular coordinate system, uh, the the killing vector may be appear very simple, and if we choose another coordinate system, uh, will we always be able to find these some killing vectors that related to that space, even the metric is written in some other coordinates?
Yes, the answer is, again, our definition is coordinate independent, okay, of an isometry. It doesn't care about your coordinate system that you use. So you can use any coordinate system. You will find this the same set of killing vector fields. They may look different because you're expressing it in a different basis. But the way to check is that Lie algebra of the Killing vector fields will be the same in any basis that you use, because the Lie algebra is basis independent. Well, okay. I mean, so you have to find Lx, Ly, Lz. Okay, there is a matching that needs to be done. For example, in SO3. No, okay. I mean, again, the starting point was that, it really is basis independent. Okay, the definition was that you preserve the metric. Okay, and when we say preserve the metric, this preservation of the metric is basically the statement that this tensor, okay, at P is the same as the pullback tensor. Okay, and that statement of tensors being equal doesn't care about what coordinate system you use to describe those tensors. Okay, so now the thing is that this coordinate chart that you use here, psi, and the coordinate chart that you use here, phi, these can be different. In which case, let me give an example. Let's do R2 with polar coordinates. Okay. If you do R2 with polar coordinates, okay, so R2 with Euclidean coordinates, we've seen that you have these are the Killing vectors, partial x, partial y, and you have a rotation operator, which is minus y partial x. So a rotational Killing vector, which is this. Okay. If you use polar coordinates, okay, that is you use r theta. Okay, first of all, this is a coordinate patch which is not valid at the origin. Okay, it's not smooth at the origin, but if we exclude the origin, we can still find Killing vector fields associated with this. Okay, now the span of this, okay, if I take linear combinations of these, that's called the span. Okay, the span of this generates this all possible Killing vectors. Okay, or all possible Killing vector fields. Now, what we can do is we can find Killing vector fields, okay, expressed in terms of partial r and partial theta. Okay, so for example, the rotation operator, rotational Killing vector would be partial theta. Okay. Similarly, it turns out that you can just perform a trivial coordinate change to express partial y in terms of partial r plus partial theta with some coefficients. Okay. I won't write down the transformation, but you can find a transformation like this. This will be some other particular linear combination. The Lie algebra between them. Okay, so if I call this T1, T2, and R, these are my Killing vector fields. I can express them in any coordinate system I like. Okay, I can take linear combinations of them and that's still a Killing vector field. And so maybe when I solve the Killing equations, I might not find this particular combination. Okay, I might find some other linear combinations. Okay, but that's okay. Ultimately, the way to check is that at the end, there should be some basis in which this this Lie algebra, okay, in some basis, this Lie algebra should be satisfied. Okay, you should be able to find a basis, a linearly independent basis in which this Lie algebra is satisfied. That is the test that two spaces have the same Killing vector fields. Okay, and the answer is that does not depend on your coordinate system.
Okay, sir.
Any other questions?